Hello students. So I will start second order reaction in this lecture. In second order reaction, repeatedly these two questions are asked in previous 10 to 12 years. Now let us take a look on this question. See, in this question he is asking for the rate constant of a second order reaction if both the reactant have same initial concentration or if both the reactant have different concentration. One more type of question which can be asked: show that the second order reaction half-life is inversely proportional to the initial concentration of reactant. That is, for second order reaction, T half is inversely proportional to 1 upon A naught. Now, what is second order reaction? We know that the reaction in which rate is directly proportional to the square of concentration of reactant if there is only one reactant, or we can say that the rate is directly proportional to the product of concentration of two different reactants. For an example, we can say that ester hydrolysis in basic medium is an example of second order reaction, as water molecule have effect on the rate. But in acidic medium, as we already discussed, ester hydrolysis in acidic medium is an example of pseudo-first-order reaction, because in that case water molecules are present in excess, which does not affect the rate. But in case of basic medium, rate depends upon both ester as well as water. Similarly, another example is gas phase decomposition of nitrosyl bromide. When nitrosyl bromide get decomposed, it produces NO and Br2. This reaction is a second order reaction. So these are the examples of second order reaction. Now let's start the proof of how we can calculate the rate constant of second order reaction, or what is the half-life of second order reaction. For this purpose, we need to assume a second order reaction in which two different reactant A and B are present and both are having same concentration. Here we assume A and B, both reactant have similar concentration of A. After some time, when X mole of A get converted into product, at the same time X mole of B also get converted into product. So the rate of reaction can be given as, in terms of A, that will be equal to minus dA by dt. In terms of B, that can be equal to minus dB by dt, or in terms of product, we can say that dP by dt. So we know that rate is proportional to the concentration of reactant raised to the power 2, which means rate is given as whole square of A minus X. So we assume the concentration of product as X. So we can write dx by dt is equal to K2 A to the power A minus X to the power 2, where K2 is equal to second order rate constant. If we plot the graph of rate versus square of concentration, Don't forget, A minus X will be the concentration of AT, or you can say BT, that is concentration of B and A at any instant T. The graph will be a straight line passing through origin. Now, basically, there are different methods to find out the value of rate constant, but I'm using the best one. Now, separate the variables in order to integrate this equation. To find out the value of rate constant, we need to integrate this equation. Now, those who are from math background, they know that integration of, say, 1 upon x square will be equal to minus 1 upon x. So applying this formula, we find that the value of integration of 1 upon a minus x square will be equal to minus 1 upon a minus x, as we are also assuming a minus x is equal to t. So we need to differentiate. So we'll find that minus 1. For better understanding, we can say that a minus x is equal to t here. When we differentiate this, we will find that dx minus dx is equal to dt. So in place of a minus x square, we can write 1 upon t square. In place of dx, we can write minus dt. Now, if you integrate this, you will find that the integration of t square is minus 1 upon t. Hope you understand this step. This is just for the integration purpose. These are the general formulas. Don't assume this is general value of x. This is not the concentration of product. This is general x, and this is general t, not the time t. Now, I stand for integration constant. This is not the definite integral, so we must need to add one integral value, integration constant. So to find out this value, use this boundary. We know that at t is equal to 0, that is at in starting, we find that the value of x is equal to 0. So put this value in this equation. You will find that I is equal to 1 by a. Now again, put the value of I in this equation, say 2. Put the value of I in equation 2. This is the equation for the rate constant of second order reaction. This can also be remembered as you know that AT is equal to A minus X. It is the concentration of reactant remain after some time T, and A naught is assumed to be the concentration of reactant initially. Now we can write this equation as, if we compare this equation from y is equal to mx plus c, we found that the graph of 1 upon AT versus T is a straight line having slope equal to the rate constant and intercept is equal to 1 upon A naught. So we prove here the value of rate constant when two different reactants have same concentration. I think you are getting my point, what I'm trying to say here. If we want to plot the curve AT versus T for the second order reaction, this is the graph of 1 upon AT versus T. This is the graph of AT versus T. You find that if you compare this graph with first order, this is for first order, this is for second order. These are the graphs related with second order reaction. Now, as we already discussed initially, that in previous series also asked what is the value of rate constant when two different reactants have different concentration value. Again, I'm repeating, there are different methods to find out the value of rate constant, but I'm trying to give you the best method. Now, suppose another second order reaction in which both reactant A and B having different concentration. Say the concentration of A is small a and the concentration of B is small b initially. After some time T, you can write this. Now, the rate of reaction is proportional to the product of concentration of reactant A and B. In place of A, we can write A minus X. In place of B, we can write B minus X. In place of proportionality sign, we can get the new constant known as second order rate constant. Now, rate of reaction can be given as dx by dt, where x is the concentration of product at any instant t. Now we know that for integration, we need to separate the variable. This is equation 1. Now integrate this equation. before integrating, we need to understand how to do the integration of this complex term. See, don't worry, I will explain each step. Although I'm not that much good in English, but I'm trying to speak because some of the students are belongs to Kerala. Now see, for solving this term, we need to multiply as well as divide at the same time from a minus b. RHS can easily be integrate. I is the integration constant, you know that. Now, see, a minus b can be written as we add x and subtract x at the same time. See, you can write the direct value also, but it is better to write the solution also. Take negative sign as common here. Now, a minus x divided by this term as well as b minus x divided by this term. I forgot to write dx here. Now we know that integration of 1 upon x is equal to the ln x, but here the value of x is b minus x. So a negative sign must be come there. So we can write as ln minus of ln b minus x minus ln a minus x you can directly use this formula. If you don't remember those steps, now apply the property of log, which suggests log m minus n will be taken as log m upon n. So now we need to find out the value of I. For calculating I, we need to put these constraint that at any time t, initially when t is 0, x will be 0. So we find the value of I. Now put this value of I in this equation. We can write this equation as, we take 1 upon a minus b common from both the part. Now again apply the property of log, which suggests log m into n will be log m plus log n. So we can write, sorry, I did a mistake here. When you take this term, this side, this will be taken as negative. So rather than multiply, they get divided. As we know that in ln m minus ln n will be ln m upon n. So the final outcome or value of rate constant when the both reactant are having different concentration. This is the scenario when the concentration of A is more than B. And if we are assuming the concentration of B is more than A, then this equation can be given as, hence we prove the point how we can calculate the value of rate constant when both the reactants are having different concentration. Now let's plot a graph. This can be written as K2T into B minus A. If we compare this equation from y is equal to mx plus c, taking time and on x-axis and this log term on y-axis, you will get a straight line passing through origin having a slope of K2 B minus A. Don't forget A minus X is the AT concentration of reactant remain at any time T. Similarly, B minus X is the concentration of reactant B at any time T. And the small a is the initial concentration of A, and the small b is the initial concentration of B. Now we need to find the half-life value, as we need to prove that half-life is inversely proportional to the concentration of reactant. Now again, we know that the definition of half-life suggests that it is the time at which the concentration of reactant become half of its initial value. So when T is equal to T half, what happens? AT is equal to A naught by 2. So we know that for a second order reaction, KT can be given as now place T half in place of T and put the value of AT. Hence, this equation proves that T half of a second order reaction is inversely proportional to the initial concentration of reactant. Okay, so we are done with the zero order reaction, first order reaction, and second order reaction. Now, what if the order of reaction is greater than 2? In such case, I'm writing the direct formula which you can apply. Although no question is asked in which the order is more than 2, but as a precautionary measure, we can write the general expression for the nth order reaction, where you know that the meaning of each and every term used in this equation. N stands for order of reaction. Similarly, half-life for the nth order reaction can be calculated by using this formula, which suggests that T half is inversely proportional to a to the power n minus 1. Now we need to discuss the problems, numerical problems specifically, which are asked from second order equations. I will make a separate video on that. Till then, you need to wait. Thanks for watching.